All right, well, welcome everybody to Primetime at the library. So just the introduction to Primetime is a celebration of learning in and beyond the classroom for Bethel faculty, staff, and students. Today's presentation is sponsored by Faculty Development and Friends of the Library. So today we welcome Sara Wyse, Danny Swensen, Amy Dykstra, and Adam Wyse. And I'll just moderate this discussion on using R. It's a tool for statistical computation, data analysis, and graphics. So without further ado, so I'm just going to start. I look out and it looks like most of you are at least somewhat familiar with statistics and the programs, but I'm going to speak a little bit to the people who are unfamiliar with even software, just what is R, just briefly. I've just been trying to learn it recently so I can speak from sort of a beginner standpoint. So just a little bit of the background. So R was created in 1993. It's generated by two statistics professors at the University of Auckland, New Zealand, and they generated it for their students to use. So even from the beginning, it was made for students to use as well. In 1995, it was actually people encouraged them to offer it up as free open source software, which means anyone can use it, but also anyone can modify it too. So there's some benefits and drawbacks to that, but there's a lot of benefits. And then as it developed later, it became a core group of people are maintaining the software as the source. So it is maintained by a large group of people, and that has continued to grow. And then in 1999, there was a global or comprehensive R archive network was founded. So global, so basically they hold the files of that source code in multiple places, so that's both maintained and preserved for a long period. So we'll flash forward to 2018. So now there are 49 countries that have what are called mirror sites, or all these archives that have the software stored and maintained. And then we'll talk a little bit more about this later, but for those who are not familiar with software, there are packages that you can add. So this software works in a basic level, but you can also add a bunch of things called packages to them. So just why R among all these other things? There's a lot of great tools out there for statistics and data analysis. This first graph, there was a study on the job boards. So Indeed.com is one of the many different aggregators of job positions. And as you can see here, R is the fifth top software package that's used and asked for in these job markets. So particularly in the data science job market, and we can talk about more about that is. But and then in the second one, the same person, he studied scholarly articles in the year of 2016 and how much R occurred in these scholarly articles as well. So it was the second one. So and then you'll see it appear within SPSS and ASS and STAT, so a lot of other statistics programs, but those are also commercial. So this one's free. So it is important in both industry and academia. So what is R? It is a programming language, it's also a software, and it's also a network of support. So for those of you who are concerned about software, there are ways to get, or command line or programming, there are ways to get into it without having to know too much. And then just lastly, so it is a base software, so at its base level, it has statistical analysis capabilities, it has graphics capabilities, but then these packages we were talking about, you can add additional things, and there's something in the archive, there are 37 different task views, they call them, or topics, or ways you can use R. So just some of those are, you can use it for web and social media when you add some capacity, there's machine learning, econometrics, finance, medical image, graphics, spatial data, and many more. But so then what you can do is you take these packages, and then you download them, add them to your base, and then onto your computer, and then you have those capabilities as well. So that's just a quick overview of what it is, how it works. And now you can, the people who are using it can tell you. Dan, you got it.
Well, good morning. My role is to sort of have us think about what an application might look like in a class. And so I used R in a couple service learning projects in a statistical analysis course I taught here, and just wanted to share some of my experiences and sort of how I approached it. I have more information I'm going to share here, but basically the two service learning projects that we did over a couple of years, where one was with Treehouse Organization, and their mission and vision is up here, and then we did a second one with Trout Lake Camps in terms of looking at some of their data as well. So one reason I decided to go ahead with service learning projects, and I'm going to talk just as much about the projects as I am R, because in a classroom application, the application is very important, and R was just a tool for us to facilitate this work or research that we're doing for the organization. So the first half, the first couple minutes, I'm just going to talk about the projects we did, and then at the end I'll come back and look a little about how we've incorporated R. So we developed relationships with both these organizations. One thing I really wanted to do is sort of try to follow the research that indicates, especially in math and statistics education, that use of service learning projects is really powerful in terms of student engagement, student learning. And it really, the beautiful part about it, it really connects well with our vision and core values at Bethel, right, in terms of serving others, and what a great way to do that. And so as I did these projects, I really saw a big difference in engagement and achievement. And in terms of, I gave a national standardized test that at the end of the course, and I even saw improvement in that in terms of student achievement. So just really quickly, Treehouse wanted us to use both qualitative and quantitative approaches to address their programming, right? They gave a survey with dozens of questions, I think over 50 questions, and they wanted us to help them look at that data and see if their program is effective, and also help them think about how and what data could be used to, for their donors or potential donors, right, to promote their program and to raise money. The interesting thing is they had actually paid $10,000 to a firm previous years to do this, so we were actually, the students were really excited that we're actually doing something that made a big difference for them, right, because they didn't have to pay that year, right, because we were doing the work for them. This was actually inspired by Dr. Wyse, right? We talked a lot in those days about teaming, what that looks like, semester-long groups. We didn't quite do semester-long groups, but we definitely did groups, long-term groups for this project. We had 7 teams of 5 students. They had a team leader, and then they also had someone specifically that was responsible for the R part, right? In this course, R wasn't really, I didn't want to teach R. R was just a tool for us, so I designated one person who volunteered for that position on the team, and that really worked well in terms of them taking the lead and making sure they knew how to do it, and in terms of analysis of data. Each member had a unique role, so everybody had a role, and one was R here. Trout Lake, same type of thing. Yes. In terms of breakdown, right? So both projects, these projects were different semesters, right? So different courses, but sort of the same setup for that as well. Trout Lake really wanted us to look at their fundraising efforts, right? And provide fundraising strategies, what was being effective, right? And they, based on their contact with different groups, how did that affect it? The content, did letters or emails work better? Did targeted emails about the scholarship fund or the activity area appeal or links to social media, right? All those different things, they wanted to see how those pieces are working in terms of the money those were bringing in, right? How effective were those? And even the type of delivery, did it make a difference in donations if they sent things by email or by snail mail, right? So they're really trying to figure out how to best use their marketing money. And so we worked with them to statistically look at some of this and try to give feedback on what was working and what wasn't. So how did we bring R in? Well, like I said before, so each team had an R representative, more than just that team member working on it, but they were sort of the point person. And so if they had questions, they'd come to me. That way I could work with them on that. There's obviously good YouTube videos that supported that, and I provided the sample R code. Again, I was just trying to use R as a tool, so it was fine. I just provided the code and they could substitute, right? So I'd give them information like this, and in terms of that would be a basic thing of how they could import their data sets, their Excel documents into R. I'd give them code like this that this would be an example, right? That in this case the data set's GPA, the Excel file survey, and so they would just have to go through, use the same code here, but they would just substitute the name of their file, the name of their data set in for that, right? So that I just gave the code, and that worked really well. I really had very few issues with this because with the point person leading and the sample code, that worked really well. And even with the graphical representation, right? So back here you're seeing some numerical descriptions. Here you're seeing the code for the graphical description. So what that led to then is really nice ways to get data, right? In terms of summary statistics and graphs to argue whether, in this case, whether or not the distribution has approximate normal distribution. We're doing that to see, this would be a practice one we went through to see if the t-test, the one sample t-test was appropriate, right? And so we would start with that. One thing I really noticed with use of R and the data, and specifically the graphs, it really promoted mathematical discourse, right? So you're going to see that in terms of the teams, that how they talked about the information, but also how they wrote about it. And I have a couple samples of that. But here's some of the, for example, the graphical pieces that we got box plotted. And then this is actually student work, right? So they would summarize what they saw. And so these aren't perfect, but I brought up just solid students. This is the first time thinking about it, but they're writing about statistics. They're looking at the graphs, and as a team, they're coming up with conclusions, right? And I really thought it was powerful, right? That mathematical statistical discourse, which is so important. And it made a difference that there was context to it, right? That we're doing this for a project. It just wasn't numbers they were doing, the numbers had context. Then like a histogram of this data, and then a density plot, QQ plot, and then again, there are descriptions of those, right? In terms of what they mean. So R really gave us nice, clean, graphical, numerical data that they could really reflect on. And then in this case, making a conclusion about whether the one sample t-test was appropriate, right, based on that data. So that's how we used R. This is just sort of a run through for them, and then they would do similar things with the data they had and what type of tests they're going to use to give feedback to the organizations. I guess that's it. We're doing questions at the end, right?
Yes.
Okay, so hi, I'm Sara Wyse from biology and also faculty development. I have used R several times with my upper level students. I am toying in conversation with Amy about maybe starting to use it with our 100 level students. So the context for my reason for bringing it into my upper level ecology courses surrounds the movement in ecology that we refer to as big data. We are sampling data across the globe on the second basis, right? With a lot of our eddy covariance towers that are collecting carbon dioxide values. And then we have a whole bunch of long-term ecological research sites that are located primarily in the US, but outside, that have been in existence since the mid-'80s and are standard at collecting various measures of the environment related to photosynthesis, related to nitrogen levels in the soil, and so on. And so we have repositories of a ton of data. And a lot of ecology right now is starting to ask longer term, bigger scale questions. So in order to prepare our students for that in their future careers, they need to have a handle on that now. And that was my impetus for getting into using R, because R is great with large data sets. Now, students can't really jump into coding right away, and so the tool that I found most useful in R was a tool called R Commander. And Amy's going to talk a little bit about R Studio, but R Commander is phenomenal because it has the user interface of a point-and-click drop-down menu, much like you'd find in SPSS or JMP or some of the other softwares that we would use with our students. And so the neat part is, in addition to the point-and-click, the code is showing up for them to see. So I had students that were really interested in learning the code as they were doing the point and click, and then they were able to take some of those skills and try running their own code as we went. But I did not take an emphasis on teaching the code. I said, let's use this tool because it's really powerful, and we'll use the drag and drop menu so that we can actually accomplish the analyses that we want to. Most students in biology have taken some level of statistics, but it's maybe been a couple of years, not super familiar to them, and so we wanted to start basic, and so really the intentional design that I had was scaffolding. I wanted to start my students at a really simple level using R and getting information from it, and then building complexity as we went through the semester. So my course is really built around now 6 big data analysis assignments. And they start really small and build towards the end of the semester where they're actually using R to compute regressions. So here's an example of an assignment for where we might start with the students. They were given data from one of the LTER sites. They're given the context of this longitudinal research that has been conducted over the course of time. And in this particular case, they were working with tree species. And they were working with the Kellogg Biological Research Center, which is located in Michigan. And then their first task was to find the data set, open it, and just familiarize themselves with data. They need data handling skills. And so it was simply open it up, let's see what kinds of headers you have. They've probably never seen variable names that quite look like these. So even that is an adjustment for them. They mapped onto that really well, and then their first task was to run some descriptive statistics, mean biomass, sample size, and standard error. And that took an entire class period, just 70 minutes trying to get into the data and run these simple descriptive statistics. But then once they had actually had their computers out in front of them and ran through that, they were curious about the data because now they're starting to see patterns. Why is it that these data look this way and this tree species looks this way? And that prompted them to go through the rest of this activity, which involved making some graphs. Moving a little bit more complex, they've used R a handful of times, and this time we're getting data from another long-term ecological research site, and instead of giving them the description of what they need to do in a step-by-step fashion, this time I just gave them the hypothesis, and I said, okay, so are these data supporting or rejecting this idea in ecology? What do we see in the data? And so this time they got to go through and decide how they were going to analyze their data in conversation with me, then execute that as they went. And then finally, the students culminated with a research project out of some of this big term data. And so this student group did not have everybody proficient in R, though these graphs are not created in R, but the data and the analysis was done in R. And so this was a result of their regression analysis, taking a look at some of the significant predictors and variables in their models. So that was really cool for them to be able to then take the skills that they had learned in these scaffolded assignments and use it to analyze their own research question at the end of the semester. So I found as a whole that using it with upper level students has been a really positive experience. I've had several that have gone on to graduate work and say, I actually know what R is and I'm using it, and that was a really helpful tool for them to have going into graduate school. I've had others that have come back and said, oh, I wish that we would have done more with R, right? Because it's a very, very useful tool. So I feel it's valuable, it's so much so that Amy and I are talking about, hey, can we do this with our intro level students and what might that look like? So I will pass it off to Amy now so she can talk about her research.
All right. Excuse me. Hi, I'm Amy Dykstra. Am I on? Good? Okay. So I'm just going to talk about how I personally used R in my research. So I'll try to put it in context of what I actually study. I study a pretty little prairie plant called Echinacea angustifolia, or narrow-leaf purple coneflower, and it's a long-lived perennial. It rarely flowers before the 7th year of its life, And it may not flower each year, and so it's kind of tricky to figure out whether this plant is persisting. So it exists in native prairies. Most of the prairie in Minnesota has been converted into corn and soybeans. So most of its habitat is gone, and so I'm interested in whether it's making it or not. So to approach this question of whether the populations of echinacea are growing or shrinking, I went out and found a whole bunch of, with help from a bunch of undergraduates, went out and found a whole bunch of echinacea plants, including some seedlings, which you can identify because they still have their seed leaves visible. A whole bunch of plants that haven't yet flowered or that weren't flowering at the time. So we call these basal plants because they have leaves from the base. And then some flowering plants as well. So you can see the leaves down here, but then the flowering stalk. So the flowers are easy to find, the rest not so much. But we tracked, I found about 950 plants in the summer of 2009, and then I carefully marked where they were using highly accurate GPS, using paper maps, and went back and found them in 2010. And so this is kind of a table that shows the fate of those plants. So out of the 65 seedlings that we identified, about, 44 of them survived. Out of the 69 flowering plants, only about 3 of them we couldn't find. One of them got covered in a gopher mound, and a couple of them died, we think. Or maybe we just couldn't find them. And almost half of them flowered again, but some of them weren't flowering the next year, they were alive. And then I had all these basal plants. So this plant, as I said, doesn't flower for at least 7 years. So it doesn't go seedling, basal plant, flowering plant. So I wanted to separate that basal stage into some more narrower categories so I could analyze their survival. And so that's where I started using models in R. Actually, I manipulate all my data in R. The thing I love about using R for my data manipulation, as opposed to, say, using Excel, is that I can keep track of everything I've done. My data file stays unchanged, and I have a record of all the code that I've used to manipulate my data, and I try to take copious notes within the code itself. So to choose a variable that I could use to separate these basal plants into narrower categories, I ran a generalized linear model, which is abbreviated in R code as GLM. And specifically, I did a regression of the proportion surviving based on the leaf count. So we measured several things in these plants. We measured the number of leaves. We measured the number of rosettes, which is a cluster of leaves. We measured the length of the longest leaf. And I wanted to see if one of those would be a good predictor of whether they survive or not. So I'm going to switch over and show you a little bit of code. First I have to wake my computer back up. So we're getting there. Here we go. Here we go. So this is what R looks like if you use R Commander. I'm sorry, R Studio. Sarah showed us R Commander. Thanks, Adam. So this is R Studio. I've started an R session, and I have all my code up here. And anything that has, this is probably really hard to see, but anything that has a hashtag tells R that that's not code, that's just notes. So it doesn't read the hashtags, and if I press this run button here, it will just run the next line of actual code. And so I like to put a date at the beginning of my file, and then we talked about how you can have different packages and different libraries. So I'm telling it that I want to use this particular library called Mass, which I'll need for some of the statistics I'm going to do. I have a line here that tells it where to look for certain files. So this is set working directory. And it's actually easier to do that by just finding it in this window here. So I know my data are in this folder here, and so I can just go in here, go into my tools here, and just set this as my working directory. So then I'll skip over that, and then I'm going to ask it to load my data. If I can click on that. So now my data are loaded onto this R session, and you can see what's in the environment that R is working with in this window. So I'm not going to show you every line. Let's see. So I want to go down here. So I made a subset of my data. I'll skip down to about here. I can run this whole set of code if I just highlight a bunch of code. And then I want to run this next one. This is a table showing what happened based on the number of rosettes. So this is the number of rosettes, the number of clusters of leaves, and these basil plants, and the status of them in the next year. So as you can see, they're more likely to flower if they have more, if they're bigger, basically. So I went through a number of, let's see, I went through a number of, actually I'll show you some of these graphs that I made. Yeah, I'll show you some. So I'm going to run this, and then I'm going to show you another graph that I made to illustrate, to demonstrate to me what was happening with these data. So again, this is the rosette count. A rosette is a cluster of leaves. Based on the number of rosettes, this is the fate of plants. So this is plants that we found in 2009 that were basil, and then this is what they were in 2010, and this is the rosette count. The next graph actually shows it a little bit better. This separates out the flowering of it. So this is leaf count, and you can see that the flowering plants were much more likely to have a higher leaf count than a lower leaf count. So eventually I decided that leaf count was going to be my best variable to use to pick a state as a state variable that would help me separate out these basil plants into smaller categories. As I was thinking about what I was going to show you last night, I was imagining people's eyes rolling back into their, which is happening a little bit. But I want to show you one more graph. Actually, I'll show you two more graphs. Here. And actually, it's probably going to take a minute. So here's a graph that shows the leaf count in 2009. And this line again is the it's the prediction based on, okay, so let me back up. So I fit a model to my data, and then I asked R to predict based on that model what would be the likely proportion survival at a particular leaf number. So that's kind of the line that shows up there. Now, just to show you a little bit more of R. So you can plot graphs in R, and if you're using RStudio, you can just kind of scroll through your graphs by using this arrow. So I made this graph, I made this graph, I made this graph, I made this graph, so you can just kind of scroll through. Now, if you don't remember, now, how does this graph compare to this graph? Is this one better? So I did some statistics as well as plotting these graphs, but it's nice to just have the visual. Okay, enough code. We'll go back to what I used this code for. Oh, it's over here. Here we go. Okay, so basically the goal of all of this was to figure out how I could divide up these basal plants into smaller categories. And I eventually determined that I needed about 4 stages of basal plants and then the flowering plant to capture my data accurately. So a seedling will become a basal plant or it will die. The basal plant can stay as a basal plant that's small, 1 to 3 leaves, or it can grow into a larger basal plant, and into a larger basal plant the next year maybe, and then into an even larger one, and finally it might flower. So if it grows every year, this is what the life cycle would look like. Or each of these can stay in those stages for multiple years. So the little plants, the 1 to 3 leaf plants, often just stay as 1 to 3 leaf plants for a couple of years, or they die. And it turns out with plants don't always grow. So this is a plant that the above ground part dies every winter, and then it grows back from a taproot. So the next year it can be smaller, so they can actually regress in size, and they can skip stages. So, so to kind of evaluate this, I calculated what percentage of the seedlings survived. About 66% of them, about 2/3 of them survived. What happened with the small basal plants? Well, about 2/3 of them just stayed as small basal plants. A few of them got bigger. One of them flowered. One of them jumped a stage. I don't really know why these two numbers are different. It seems like it should be the same. And then a certain percentage of them died. Okay, so I could put in those numbers for every stage and try to figure out, okay, what's happening with my plants. But the whole goal is, or it's easier to look at if you just put it in a matrix. So this is a population matrix, a population projection matrix. And what I have here is the status in 2009 is shown in the columns, and the status of these plants in 2010 is shown in the rows. So all the plants that were seedlings in 2009, none of them were still seedlings in 2010. 2/3 of them became basal plants and the rest died. Of the small basal plants, 2/3 of them stayed as small basal plants. A few of them got bigger, and there was even 1 or 2 that flowered. So that's kind of how this chart reads. And this number up here shows you the proportion per flowering plant of new seedlings in the next year. So for every 4 flowering plants, we found about 1 new seedling that came up. Not very many. Now, the whole purpose of doing this is to do some matrix math on it. So you can ask R to do some matrix math for you. There's a package called PopBio that does this automatically. And you just tell it what the matrix is, and you ask it to do some matrix math. And it turns out that the dominant eigenvalue that you can get from this matrix is a prediction of the population growth rate. If the population growth rate is 1, the population is staying the same. If the population growth rate is below 1, it's declining. So the prediction that I got is below 1. Then I did some more math to figure out how confident I could be in that data. So I used R to do bootstrapping. With bootstrapping, what I did is I generated sample data sets by sampling with replacement from my data. So I've got 900 plants, and I sample with replacement to create a new sample. And then I do that 3,000 times. So I've got 3,000 matrices, and I calculate 3,000 population growth rates, and I figure out what the 95th percentile of that is, what my confidence interval is. And it turns out that the confidence interval did not overlap with 1. So it's kind of bad news for echinacea populations. Second thing that I was really interested in was whether the size of the population remnant made a difference. And so I divided my data into the large populations and the small populations, and I made 2 separate matrices, and it turned out that the large population matrix, that was better. The confidence interval almost overlapped with 1. It was still different than 1, but it's close. So the small population data, small populations were actually declining at a faster rate, it looks like. And to figure out if this difference was significant, I did randomization testing, where I did a different kind of sampling, where I took my data and then I just randomly, instead of assigning plants to the actual prairie remnants where they live, I randomly assigned them to the large or the small matrix. And I did that 3,000 times, so that I generated 3,000 large and small matrices and calculated the difference in lambda for each one of those. And there's a lot of complicated math for, not complicated, but stuff you don't really need to know. But my test statistic was difference between those 2 population projections. And it turns out that there was a p-value of 0.001. It's very unlikely that I would get as much difference as I actually saw based on my results. So, okay, I can do this. I'm going to skip over this. And I will just say, this is all about R instead of my data. But what I love about R is, like I said before, I can do all kinds of things in my code, and I can save that code, and I can know exactly what I did. R can handle big data sets. I had 900 lines of code. It's hard to sort of get your mind around that. If you're working with Excel, you can't see it all. And you can do these iterative processes. When I would set up R to do these randomization tests, for example, it would take a couple hours, and I could just walk away and let R do it instead of me doing all that sampling by hand. And I'm sure I'm out of time, so I'm going to turn it over to Adam.
So my name's Adam Wyse. I do occasionally teach here in the education department. Although what I'm going to talk about today is not necessarily that, but some of my other work, which is my primary job, and I am a psychometrician, so I use R all the time, every day, for a lot of different things. We don't have a ton of time, so there should be some time for discussion, so I'll probably skip over some stuff. Some of the stuff we already talked about, but there's a lot of different ways you can run R. And I think you're kind of getting that from a couple of the previous presenters. You can just do it on your regular desktop using Editor or Notepad. You can run it with our Commander, which is often probably the most useful for teaching kind of applications, because students really don't, unless they're having a lot of programming capability, they typically don't have a lot of the background for that. Another option is something called TinR with R installed. That is kind of useful if you like to use 2 monitors. I find that to be kind of a good kind of option if that's what you like to do. It has some really nice things if you're primarily a coder. RStudio, which is probably the most popular way to do this in business. You can either use it from desktop or via server. And oftentimes when you have really, really big data, like the stuff that I would be dealing with, the server would be the option that you would actually be using, like gigs and gigs and gigs and gigs of data. And you can also run R from a lot of other different software packages if you want to do that, and there's often reasons that you want to do that functionality when you're in business. I'll just skip over all the different ways you can do that. You can just see quickly how you can do all those different things. And then I'll just show you some different things that you can actually do with it, and these will just be applications that I've done. So this first one is just shows you some examples from an area that I work on called standard setting. Typically you get a group of people together, they're giving ratings and they're making predictions for where they think people should pass and fail different tests. And you go through multiple rounds of the process and you provide them with feedback. And these are just examples of feedback information that you can give to panelists when they're actually doing these activities. And what it's showing you here, ideally it should fall right up along this straight line, and it's showing you that they're overestimating certain difficulties and they're underestimating other difficulties. So you can see hard items, they tend to overestimate the difficulty of those, and easy items, they tend to underestimate it. And we can actually provide that as feedback in a scatter plot, or this graphic right here, which we call like a balance plot. And we can tell them specifically what items, if they're going through and viewing test items, which items they should actually take a look at. And we can create all kinds of different graphics in R. It has a lot of capabilities to do that. And all the examples I'm going to show you are just various graphics associated with different things that I've actually done. So here's an example. Another example from education. One of the popular things that they do is they do growth modeling, and there's different ways that you can actually do that. One thing would be called a transition table, which is over here, and then we also have like student growth percentiles that we could actually do too, and we can create graphics that communicate information about how students are growing or learning and different things like that. So this would tell you, this graphic will tell you the bigger letters tell you where the status of most of the students are, so most of the students are here in the proficient and advanced category. And then you can just look across and see where the greatest shading is to see where, when they go from one year to the next, where they actually are. So we can see most of the students are maintaining, and actually getting a real significant decline there is not very common. These are just more examples of graphics that you can kind of do. You can get really kind of sophisticated, and there's lots of different things that can kind of come out. You can do bubble plots, you can create these and put these into PDF graphics, Windows media files. The possibilities are virtually limitless of what you can actually do. And you know, it's basically up to what you can actually think of is what you can kind of come up with. This is from job analysis. So I won't kind of go through all these. This would be an example from like computer adaptive testing, where you want, you know, the item that's actually getting selected to be close to the target location of the ability of the student. And what you can tell here is this particular computer adaptive test for a high ability student isn't actually working the way that you would want. So we can actually go through, depending on, you know, what kind of application it is, we can create graphics, we can create statistics, and we can do a lot of different things with R. And so it really is up to you and the functionality of what you want to actually do with it as to what it can actually do. So I'll just leave it at that.
All right, well, first of all, lastly, I'll just say, one of the reasons, or one of the goals of this is to just build a community among Bethel, people who are using it, using R for different reasons, everyone wants to learn, who's curious. So that's also, if you want to learn more, of course, continue the conversation with today's panelists. Bob Kistler already created an article on using R and starting out with R on the TLT site. I've created a Linda playlist of some of the different R modules, and data science is a larger context. And then also, there's a link here on this if anybody's interested. If you are interested in maybe continuing the conversation, maybe you can add your name to the list and maybe see what the next. But other than that, any questions, comments on how you've used it? Yes.
I have a question. So our class applications are MATLAB. That's what our alumni are often using in their companies. So for us, it's less data analysis, less statistics, and more vector matrix manipulation, modeling, background subtraction, fitting. How well does R adapt to those things? For instance, one experiment that I have people do is they first need to take in, 100 gigabytes of data, and they need to loop over them, calculate new variables from the variables in the data set, and then select on those new variables and then start plotting them. So does that have equal built-ins to what MATLAB or Python would have for R?
I think so.
Yeah, you could do all those things. I think one of the things to know about R is looping is typically can be slower than in some other languages, so that's kind of important to know. One of the things you can also run into, depending on the size of the data, is you can run over the memory limit. So that would be kind of the situation where you'd want to be using it with like a server, because a server actually has, typically a huge kind of capacity that you can kind of have there. So it can do all the things that you're actually talking about. It just may be that it may not be as fast as MATLAB and some of those kind of looping type applications. But it is free and MATLAB isn't.
That's not a small thing.
And it has a lot more functionality than MATLAB does.
Yeah, I forgot to mention that almost everything I know about R comes from the R book. And this book was really helpful for me for some of that matrix stuff that I did. And this is in the Use R series, so I wouldn't be surprised if there's a Use R book for the kind of things that you. So this is a Springer publication.
And there is like on the R, there's a site called R Project, which has all those archives, and then there's one that's called a task view, so it has sets of packages, and there's one that's computational chemistry and physics, if you haven't seen them, but that also may have some of the materials there too. Other questions, comments? Well, thanks for your time.
Yeah, thanks for
Thanks to
coming.
all of you for sharing your experiences.